Hello everybody, Hobo here, and today we'll be discussing a numerical method known as the Newton-Raphson method. Now you might ask what a numerical method is, and the simple answer would be that when an equation is too hard to solve, or when any problem is too hard to solve, we can approximate the solution to astounding accuracy by just employing a certain algorithm. So today I will show you a problem which is definitely hard to solve, theoretically, and I will show you the numerical solution. So let's start out with the question, for what x does sine of x equal the square of x? And seems very difficult, but we can manipulate it algebraically and get sine of x minus x squared is equal to 0. And then we can try to find the roots of this function here. We can say that this is equal to f of x, and we can try to find the zeros of this function. So let's try to find out how to do that, because it doesn't seem apparent immediately. So to find the zeros, we'll need to employ the Newton-Raphson method. So let's say that we have some arbitrary function f of x, and we're trying to find this root of the function over here. And so what we'll start out doing is we'll start out choosing an arbitrary value close to our root. We can try and graph it and pick any x value which seems close enough to our to the root that we're trying to approximate. And then we can take the point on our function which satisfies this x value as a1 comma f of a1, if our initial point that we picked was a1. Then what we will do is we will take the tangent line to the function at this point, a1 comma f of a1, and then we'll see where the tangent line intersects with the x-axis. And then this point of intersection will be defined as a2, and then we'll do the same strategy. We'll pick a new point on our function, which is a2, f of a2, and then we'll take the tangent line there, and we'll see where it intersects the x-axis, and we'll iterate this process 3 or 4 times to approximate our root with some accuracy. So if we work this out mathematically, we get something like this. So keep in mind that we started with some a1 value, and then we described the point as a1 comma f of a1. Now the slope, the tangent line of our function, the slope of the tangent line will be f prime of a1. And we don't want only the slope, we want the actual equation of the tangent line so that we can calculate the intersection point of the tangent line and the x-axis. So once we know the slope and the point which the line goes through, we can use point-slope formula, which says that y is equal to the slope, which is f prime of a1, multiplied by x minus a1 plus f of a1. And we're trying to calculate the intersection point. So the x-intercept will mean that the y value equals 0. So therefore we're trying to solve the x value for which this equation holds. And with some literal algebraic manipulation, we get f of a1 So f a1 into f prime of a1 minus f of a1 divided by f prime of a1 is equal to x. And you can work that out at home. It definitely checks out. And so now what we've succeeded in doing is calculating the x-intercept of our tangent line, the intercept of our tangent line in the x-axis. And the intercept of our tangent line in the x-axis we will name a2, and we will iterate the process. So this entire expression here effectively becomes our new a1 value. We call that a2, and then we'll plug it into the same exact expression, and we'll try to evaluate it for the new x-axis intercept, and then we'll keep on repeating this process. So now that we've clarified exactly what the method is, let's try to work with it for sine x equals x squared. Now, sine x equals x squared, there's already one very apparent solution. It's simply 0. And the graph of sine x equals x squared looks something like that. Bad graph, but that's basically what it looks like. And it has one x-intercept here at 0, and it has another x-intercept here, which we don't know, but which we're trying to approximate. Now, we do know that the value 1 lies after the second x-intercept. So since 1 is a fairly close value to our the x-intercept that we're trying to approximate, we can use it as our a1 value. So 1 is equal to a1. Now, what we can do is we can plug it into our equation f prime of a1 f prime of a1 minus f of a1 divided by f prime of a1 is equal to x, or in this case a2. And if we have 1 is equal to a1, then let's try and find a1 f prime of a1. So we're trying to calculate the derivative of the function sine x minus x squared. And the derivative is simply cosine of x minus 2x. So that multiplied by a1, which is 1, will simply yield this. And now let's try to find, with a calculator, what cosine of 1 minus 2 is. So cosine of 1 minus 2 is equal to negative 1.45. And now let's try to calculate what negative f of a1 is. That is simply the negative of the sine of 1 minus 1. So let's calculate sine of 1 minus 1. And that multiplied by negative 1 is equal to, so this value is negative 1.45. This value is equal to 0.15. And this value over here is equal to f prime of a1 is simply sine of 1 minus, f prime of a1 is simply cos of 1 minus 2. So cos of 1 minus 2 is equal to, again, negative 1.45. So this value also equals negative 1.45. Now, let us add these two. Let us add these two and divide that by this. So negative 1.45 plus 0.15 divided by negative 1.45 is equal to, so now we have our a2 value. a2 is equal to 0.8965. So now let us plug in our a2 value to find an a3 value. So what we've succeeded in doing is calculating the x-intercept of the intercept of the x-axis and the tangent line, And now we will iterate that process once more, and after 2 iterations we'll have a fairly accurate answer. So now we have a2 into f prime of a2 minus f of a2 divided by f prime of a2 is equal to a3, which is going to be our fairly accurate x value that satisfies this equation. So we will have a2 into f prime of a2. That is cos 0.8965 multiplied by, so 0.8965 multiplied by the cosine of 0.8965 minus 2 times 0.8965, and that will equal negative 1.0476. And f of a2 will be 0.89, sine of 0.8965 minus 0.8965 squared. And that will equal negative 0.0225. And then f prime of a2 will simply be cos of 0.8965 minus 2 into 0.8965. And that will equal negative 1.168. So if we plug this in and we subtract these two and divide it by this, then we get negative 1.0476 minus negative 0.0225. That divided by negative 1.168. And then we come up with our A3, which is equal to 0.87765. And we can check if this value is fairly close to equaling the x value which solves our equation. So we can say sine of 0.87765 should be equal to the square of 0.87765, and sine of our A3 is equal to 0.769, and the square of our A3 is equal to 0.77, so they are fairly close approximations. And now that we've solved the problem, we will discuss some limitations on our Newton-Raphson method. Now, because of the graphical intuition that I represented, some very apparent problems arise. Specifically, if I take a sinusoidal function, f of x equals sine x, it doesn't need to be a sinusoidal function, but a sine wave is a good example of a function where problems arise with the Newton-Raphson method. So let's say that I'm trying to approximate this root over here, which is 2 pi comma 0. No, sorry, yes, 2 pi comma 0. Now, if I take the tangent line at this point, and I see where it intercepts the x-axis, and then I drop that and make that my a2, then if this a2, if I take the tangent line of the function at that a2, and the tangent line is perfectly horizontal, if it has slope 0, then that means that I can't find any more a3, a4, a5. And it doesn't even intersect the x-axis, so it really destroys the Newton-Raphson method. And so that's why you need to pick a fairly close value for a1, which is fairly close to the x-intercept that you're trying to approximate. And another problem could arise where you might approximate the wrong x-intercept. So let's say you're trying to approximate this x-intercept, and then you take x value, let's say you take an a1 value over here, and then you calculate slope of the tangent line, it's over there, slope of the tangent line, it's over there. So then you end up approximating this root instead of that root. And that's another area where this method fails. And all of these problems can be resolved simply if you pick a good enough a1 value. So if the a1 value is close enough to the root that you're trying to approximate, then you will definitely encounter a good approximation of your root. And that concludes our portion of the numerical Newton-Raphson method. Thank you.